In lesson 3.1, we're going to make the transition from studying one variable data sets into studying two variable data sets. So in the lesson sheet you received, there's a fair bit of reading and background to give you an introduction to some of the key features of two variable data sets. I'm going to highlight some of those key features in this video, and then in the next video we'll go through some examples together. So let's begin by just looking at one variable graphs. If we choose to use an x and y axes for one variables, we know that the x variable tends to either be something that's discrete, could be something like hair color, eye color, something that's descriptive in nature, or qualitative in nature, in which case we would use a bar graph to show it, and we would graph frequency, how often a certain type of hair color or a certain type of eye color or something appears within a population. But we also learned in the last unit that we could also make the x-axis continuous, where something is being measured. In class we used our class heights of all the students. Could be something like the number of steps that you walk at school every day using your Fitbit. And again, we could group those continuous data into bins and look at how frequently a data point appears within that bin or within that range. Switching over to two variable data sets, we have a similar setup we can have with an x and y axis, and this is one that you may be more familiar with from previous math courses, but also especially in science classes in grade 9 and 10, where you have an independent variable that you choose and you choose the variables of, and a dependent variable that you measure as an outcome of your choices. This always is the way that we plot the two data sets, except if the dependent variable is time. If it's time, then time always goes on this axis, unless you're studying period length in physics, but most of you probably haven't, and so otherwise that's the only time we switch these two, is that time would always go down here. There are two kinds of correlations that can exist in two variable data sets, and in two variable data sets we always plot these as scatter plots. The first type of correlation we might have is something called a positive correlation, and all that means is that when you scatter plot the data, it seems to have an upward trend, meaning that as the value of the independent variable increases, so does the value of the dependent variable. A negative correlation is one in which there's a downward slope instead. So we would have the plot look something maybe like this. Okay, negative slope. In other words, as the value of the independent variable is increasing, the value of the dependent variable is decreasing. Now, if we can put a best fit line through these, we could call this a linear correlation. And up until now, you've probably learned to do it just with a line of best fit. Maybe your teacher said take a clear plastic ruler and try and twist and turn it, or maybe put it up on its side to try and connect as many data points as you possibly can along that line, but then to have an equal distribution of data points on underneath the line and above the line, spread out across the entirety of the line. And you may have done that and eyeballed it and maybe put in, what you figured out to be a best fit line. And I'll just throw it in here quickly without a lot of effort, something like that. Okay, this is not the best. There are about 5 on this side and 5 on this side, but I probably would have tweaked it maybe a little more this way so that there's not as much of a gap on either side with those data points. Okay, but this is just an example of what I'm referring to. Now, if I did this line of best fit and all of the data points actually ended up being on the line, I would call this a perfect negative correlation. And I would call it perfect negative correlation because it's in a downward trend. If it were a scatter plot and they were all on a line going upward and all of the data points were exactly on there, I would call that a perfect positive correlation. Now, non-perfect happens when the points start to get a little further and further away from that line of best fit. So there's a number of scenarios we can look at. We can look at something called a strong positive or a strong negative. Strong means you might have a line of best fit, maybe it even starts at the origin and it's a direct correlation. But there's just a little bit of variance away from that line, but it's pretty close. That would be called a strong positive. A strong negative would be the same idea, only using a negative slope. Okay? But if the points start to get further and further away from that best fit line, instead of using the word strong, we can downgrade it to something called moderate, or if it really looks like a scatter plot with no great line at all, we could call it really weak, or maybe even to the point of being nonlinear at all. So nonlinear at all might be something like this, where it's just points are everywhere and you go, where in the world would I do a best fit line? Should it even be positive or negative? And you might say there's no correlation between this independent and dependent variable at all. Now the good news is we can actually determine whether the correlation is strong, moderate, or weak using quantitative measures, using something called a correlation coefficient. And the neat thing about this correlation coefficient is that it can actually be calculated for a given data set. Now on page 2 of your notes and your handouts, I have a little bit of sort of a theoretical background as to where the equation for this R value, this correlation coefficient, comes from. And we are going to go through an old-fashioned way of calculating it, and then we will skip into using technology to allow it to calculate the R value for us. So R is also nicknamed the Pearson product moment coefficient of correlation. I'm okay if you just call it the correlation coefficient for short. And the neat things about this R value are, if you have a really large data set, lots and lots of points, it's actually a really reliable tool to tell you if the independent and dependent variables are in fact correlated to each other. But if you only have a small set of data points, say you've only got 5, and maybe even they're pretty close, you could get a best line fit in here, the R value might be really close to being perfect, but because you don't have many data points, it's not maybe the best tool in determining whether these two factors are related or not. The more you can populate this best fit line with more data points, the better, the more you can depend on this R value to concretely say these two variables are correlated to each other. Now the R value, or the correlation coefficient, has a range in values all the way from -1 for a perfect negative correlation, all the way to +1 for a perfect positive correlation. So you can't have an R value bigger than 1 or smaller than -1. It will be in between somewhere. And at the bottom of the first page of your notes, you will see that now, using this quantitative measure, we can actually categorize the type of correlation we have. So if we let the correlation coefficient be equal to 0, and by the way, this scale is a continuous scale, and different textbooks may have these thresholds at slightly different values, and that's okay. For the consistency of our course, let's use 1/3 and 2/3 here, and a perfect 1 over here. This would be a positive linear correlation if the R value is between 0 and 1, and as I said earlier, this would be a -1 correlation between the variables if we get into negative values of R. And now we can actually put those descriptive words in here too. If the R value for a set of data as we're calculating a best fit line lies between 0.67 and 1, we call this a strong positive. And similarly down here, we can call this a strong negative. If it's at 1, it's a perfect correlation. And similarly, -1, it's also perfect. It just means it's a downward slope instead of an upward slope. In the middle, we can use the description. It has a moderate correlation in both of these ends. And if it's between 0.3 and 0, it's classified as weak. And even though I don't have this in your notes, I would say with certainty that if you have an R value of 0, you could say that there is a non-existent linear relationship or linear correlation between the data. And this happens. This is real science. A lot of the times if you try and run an experiment on two variables, you don't always get into this strong range. A lot of times when you try to see if two things are related, you find out that they're not. And that's just as important to know as the things that are related to each other. So there's a little bit of background there in terms of where we're heading into two variable data. I would like you to go on to the lesson plans I've posted, and I would like you to also learn the key difference between correlation and causation. Correlation is not necessarily equal to causation. And there are some fantastic examples of this at the website that I posted in the lessons. But you just need to go to www.tylervigen.com. Or if you Google spurious correlations, you'll see exactly what I'm talking about. You'll see examples where a correlation definitely seems to exist when you graph out two variables against each other, but when you look at the two that get plotted against each other, you go, what? There's no way in the world, in real life, these two things can possibly be related. So I encourage you to go check this out because it's a really fun website. All right, in the next video, we'll do some mathematics of calculating R to show you how it works.